Greetings, my name is Thai-Hoa. Currently, I'm doing PhD at National Taiwan University under the guidance of Professor Jacob Lin. Today, on behalf of our research team from NTU and Delta Research Center, I would like to present our paper, Learning Basic Degree of Freedom Camera Pole Estimation using BIM-generated virtual scenes for facility management. We have learned that BIM offers a detailed digital representation of buildings, including spatial, structural, and operational data. In facility management, accurately localizing a real image within BIM provides clear spatial context, enabling managers to understand exactly what and where issues are. It has precisely allocate human resource and equipment to the required area or quickly navigate affected locations when having safety issues. However, localizing images from reality to BIM remain challenging, mostly due to poor texture in real-world images and cross-domain variants. So to address this, we propose combining BIM-generated scenes with a deep learning model to enhance image localization results. This slide summarizes traditional approaches for camera pole estimations, including PNP solvers, feature-based methods like structural from motions, multi-view geometry techniques, or model-based methods. They all use local features extracted in real images to calculate the camera poles. Although effective, it takes time to collect reality data when using these approaches. Currently, deep learning has enabled significant advancements in image-based localizations. Popular models include PostNet and its variants. While the method offers advantages such as real-time estimation and high accuracy with quality datasets, its performance remains constrained by data scarcity and cross-domain challenges. So, training pole estimation models with synthetic images offer a promising solution when real-world data is scarce or costly to annotate. Several studies have demonstrated good localization results using synthetic data. However, despite addressing data scarcity, performance can still be affected by the reality gap. The objective of our research is to develop an automated BIM-based image localization framework for indoor environments by leveraging synthetic data and deep learning. Following the framework, we will have a system that can extract essential spatial features from images captured in the inspection path. The system can bridge the gap between virtual BIM environments and real-world scenes. Also includes high-level semantic cues for better conceptual understanding. We also want to use a neural network model to predict where a real-world image fits in the BIM space. So please imagine that during a building inspection, inspectors can upload images to the system developed in this research to receive immediate feedback on their current location. At the same time, they can access BIM-related information of that location. So in real-time localization enables inspectors to quickly identify inspection points, optimizing the working routes and avoid unnecessary delays. This framework illustrates our image localization pipeline, starting with a BIM model, which is used to generate camera views and simulate a virtual environment. From this, we create a synthetic dataset containing RGB images, semantic maps, and corresponding 6GOF camera poses. These outputs are then used to train the CNN that learns to estimate camera poses. Meanwhile, real-world images captured from the actual scenes are processed in the same way, combining visual and semantic features. During inference, the chain model takes a real image, predict its camera pose, and align it within the BIM environment. In the first phase of our framework, we focus on synthetic data generations. Camera poses are generated in Revit using a rules-based system where we define camera paths and place viewpoints along them. As you see in the clip, these camera parameters are then exported along with the BIM model to NVIDIA ISARC sim for realistic workspace and camera simulation. Within the simulation environment, we generate various types of synthetic data including RGB image, semantic image, and depth image. Next, the second phase is to train a regression model, which employs a PostNet-based CNN, which is designed with 22 layers. The model takes RGB and semantic image as the inputs, so we have 6 channels in total. Input images are resized to 224 by 224 and normalized using ImageNet specific mean and standard. This ensures that our pre-trained Google Net backbone see data on the same scale it was trained on. The tensor then follows through two initial convolutional layers before entering a series of 9 inception modules. The detail of inception modules is on your right here. These inception blocks progressively expand the feature from 192 channels to up to 832 channels, capturing both fine details and global context. Two dropouts were made after inception layer 3 and 6 to avoid overfitting. After inception 9, there is a deep branch global average pooling produced a 2048 dimension descriptor which when fits to fully connected heads to predict 3D position X, Y, and Z and orientation in quaternions. During training, we minimize a combined loss using this loss function. For the experiment, an academic building in our university was selected. Following the framework, the building was then modeled in Revit and simulated in ISARC Sim. When creating camera poses, its camera position has 5 different orientations at the illustrations, making a total number of images to around 4,000. We then split the dataset into chain validation and test set with a ratio of 80, 10, and 10%. While a set of real images were also prepared for testing and comparison. Here are the examples of the synthetic and real image datasets in our experiment. While ISARC Sim automatically generated the outputs, we manually labeled the real image to ensure that the manual labels have the same color code as the synthetic training data. So when inputting semantic image to the model, the semantic information per pixel is treated like extra color channels and fused with the RGB image. After training the model, we achieved the results as presented here. The synthetic test has a mean translation errors of 5.81 meter and a mean orientation errors of 69.05 degree. Meanwhile, the real image test has got a mean translation error of 7.59 meter and a mean orientation errors of 81.75 degree. The examples down here show estimated results of a synthetic image and a real image captured in the same positions. So as you see, the prediction results are very similar with a quite small translation errors. However, the orientations are not good. More results of the estimation using real image datasets are shown here. We present both the render view of the estimated pose and the top-down visualization to help illustrate the translation and orientation errors more intuitively. While discussing about model performance, despite training on fewer than 4,000 synthetic images, the model achieved acceptable pose predictions. However, a significant challenge lies in the reality gap that includes differences in lighting, material, and object presence between synthetic and real environment. As shown here, the synthetic image lacks the details, texture, and clutter found in the real hallway. This gap particularly affects rotation estimation, which requires capturing fine-grained orientation cues often missing from virtual data. After all, we have identified two major limitations. First is the lack of visual complexity in synthetic images. Secondly, our model currently cannot distinguish between images at different floors or in large-scale workspace with similarity. In order to improve the model, in future we will add depth information for spatial understanding and extra point and light features into the CNN model. We also apply PNP and Ransack for pose estimations. To conclude, this study proposed a two-stage framework for image localization across domains using a deep learning approach and synthetic data. The first stage involved generating synthetic datasets from BIM models using a simulation tool, while the second stage trained a CNN to estimate camera pose using RGB and semantic inputs. The post-net-based model achieved a mean translation error of 5.81 meters and an orientation error of 69.05 degrees. While the model showed promising results for initial localizations, it struggled in large and visually similar areas. To improve alignment with real-world data, pose refinements using geometric methods like PNP and Ransack is recommended. Ultimately, integrating synthetic data deep learning can lead to a more robust and accurate localization pipeline. This is the end of my presentation, and I would say to thank you to your listening and also all the sponsor who has supported me in this research. Thank you.